Build a multi-role superspace rocket. In-depth guide. Multi-role superspace rocket likely refers to advanced, versatile launch systems capable of performing multiple mission types, such as deploying satellites, transporting cargo, and carrying humans, across various orbits and destinations. These rockets often emphasize reusability, heavy payload capacity, and adaptability for both commercial and scientific missions. Mission planning and requirement analysis. Purpose. Define what the rocket needs to do and what success looks like. Key. Actions define mission types: cargo to LEO, MEO, geo-crewed missions, Earth orbit, Moon, Mars, satellite constellations, deep space, probe space station docking or construction. Determine. Payload capacity, maximum mass and volume per mission type. Payload bay, flexibility, pressurized and unpressurized. Mission environment. Analysis, launch weather conditions, space radiation, and micrometeorites. Constraints, budget, time frame, safety regulations, launch, site latitude and orbital inclination access. 2. Conceptual design purpose, lay out the overall vision and modularity of the rocket. Key decisions, architecture, number of stages, 2-stage for LEO, 3-stage for deeper missions. Detachable boosters, like Falcon Heavy. Modularity, interchangeable upper stages or payload compartments. Swappable fairings for satellites versus crew module size and proportions. Consider transport, e.g. road or barge delivery. To launch site, optimize for mass-to-orbit ratio 3. Propulsion system development purpose, provide powerful and reliable thrust. Engine choices, first-stage engines. High thrust. Sea-level optimized example, Raptor, methane, Merlin, kerosene. Upper stage engines. High efficiency and vacuum example, RL-10, BE 3-year usable engine design, durable turbo pumps, regenerative cooling, reignitable ignition propellants, RP1 locks, traditional, safe liquid hydrogen.LOX, high efficiency but difficult to store, methane.LOX, reusable and easier to produce on Mars testing, thrust vectoring control, reignition, crucial for multi-burn missions, engine out capability for redundancy. Materials and structural engineering purpose. Build a strong yet lightweight structure for launch and re-entry. Material types. Primary body. Aluminum-lithium alloys or carbon fiber composites. Thermal zones. Heat-resistant alloys like Inconel or titanium reusable. Parts. Ablation-resistant tiles or SpaceX-style Pika-X shields engineering methods. Finite element analysis. FEA topology optimization, fatigue and stress testing for 100+ reuse cycles, acoustic vibration resistance. 5. Avionics and control systems. Purpose. Make the rocket smart, stable, and responsive. Components. Flight computers. Redundant, radiation-hardened. Processors, navigation systems. Inertial measurement units, IMUs, GPS, star trackers, attitude control, cold gas thrusters, gyroscopes, engine gimbals, data handling and telemetry, real-time communication with ground control software, autonomous launch, landing, and abort protocols, fault detection and correction, AI-based mission adaptability. 6. Thermal protection and re-entry systems. Purpose. Prevent overheating during re-entry. Systems, heat shield, ablative, used once, or reusable, tile-based, passive insulation. For internal components, active systems, heat pipes or phase change materials, tested with plasma wind tunnels. Suborbital re-entry flight 7. Payload and mission module integration. Purpose. Accommodate many types of missions. Design strategy. Modular payload. Adapters. Custom mounts for satellites, cargo, crew modules, life support. Ready. Interface ports for pressurized crew compartments, deploy mechanisms. Robotic arms, spring-loaded ejectors, clamp bands, compatibility. Standardize with ISS docking adapters. Interplanetary modules 8. Ground infrastructure purpose. Support safe launch and recovery. Facilities, launch pads, flame trenches, hold-downs, sound suppression fueling systems, cryogenic handling, loading safety recovery zones, ocean barges or on-land landing pads, transport, large transporters, cranes, clean rooms for payload integration. Full-scale testing and validation, purpose. Ensure reliability and performance before missions. Types of tests, tank pressurization, cryogenic fluid handling static, fire tests of engines drop tests for recovery systems, environmental. Testing, vacuum, radiation, vibration. Chambers flight
10.
test campaign,
Reusability
incremental
and
goals
turnaround.
from suborbital
Purpose.
to full missions. Reduce cost and increase launch frequency. Technologies, landing legs, grid fins, autonomous landing software, rapid refurbishment of engines and heat shields, health monitoring sensors embedded in parts roost cycle, inspect, replace worn parts, fuel, launch again, example goal, 24-hour turnaround like Falcon 9, Starship 11. Human rating and safety systems, if crewed. Purpose, protect astronauts and passengers. Safety systems, launch escape system, LES. Pull capsule away if rocket fails, redundant computers. And power systems, environmental control and life support system, ECLSS. CO2 scrubbing, oxygen and temperature regulation, radiation shielding tests, abort system tests, crew evacuation drills, thermal, vibration tolerance for life support, hardware. 12. Launch. Operations and post-mission activities purpose. Execute mission. Recover vehicles. Analyze data. Launch day. Final system checks. Countdown procedures. Remote ground control coordination. Post-launch orbit verification. Payload deployment confirmation. Return sequence initiation recovery and inspection mission. Analysis performance. Metrics fuel consumption. Anomalies and corrective actions upgrades for future missions. Final thoughts building. A multi-role super space rocket is like assembling the world's most advanced machine that can survive and adapt in one of the harshest environments, space. It requires interdisciplinary collaboration, engineering, physics, chemistry, software, massive simulation and testing, smart design for reusability and flexibility, extreme attention to safety,